In this section, we are going to review exponentials and logarithms and look at solving some of those equations that involve those types of functions. So we have b to the x equals y. If we want to rewrite that as a logarithm, we would write it log base b of y equals x. Something that helps me remember how to rewrite these here is that b and x are together whenever they're an exponential. So if I want to rewrite those as a log, then I want to split up the b and the x. So b is the base of the exponent, so it has to be the base of the logarithm. So I have log base b, and then it can't go with the x because we're trying to split those up, so the y will now go here, leaving the x on the other side of the equal sign. So before we get started with working some problems, a couple things that we have to make sure we note is we have to make sure we know how to deal with common logs and with natural logs. A common log is a base 10. That means whenever we see log written without any little number there below it, that is like having a log base 10 of 10 here. So whenever a base is not written, we assume that the base is 10. Whenever we see ln, that stands for natural log, and that is log base e of 10. E is a number, sort of like pi in a way. E is a number. If you type it into your calculator, the e is right here above the natural log, so you can say, so let's go back to the main page, second natural log e, I guess I should actually go over here, second division sign is also the e. If you hit enter, it tells you that it's approximately 2.71828, and then it continues on. So that is actually a number that we have there as the base when we have that e. So the first thing that we're going to look at is rewriting in an exponential, rewriting exponentials in logarithmic form. So if we have 6 to the second power equals 36, we would rewrite that as log base 6 of 36 equals 2. See here that the base of the exponent becomes the base of the log. The 2 goes over here on the other side of the equal sign, and a 36 is what we're taking the logarithm of. For example, 2, I've got 4 to the x power equals 2,000, so that would be log base 4 of 2,000 equals x. So that's how we rewrite our logarithmic, our exponential expressions as logarithmic expressions. Let's move on and let's look at how to write a logarithmic expression as an exponential. So right here I have log of 8 equals x. Now I don't have a base written, but when no base is written, I assume that that base is 10. So when I rewrite this, the base of the exponent will be 10 to the x power equals 8. Right now we're just rewriting, we're not going to do any solving. Here I have natural log of e equals 1. This is a base of e in this case. Whenever we see natural log, we assume that has a base of e. So we would rewrite this as e to the first power equals e. And that would be the exponential form of that equation. For the last one, we've got 3 to the third power equals 27. So that's how you rewrite from a logarithm to an exponential. Now this can be useful because it can be used to solve equations. So sometimes we're given equations like this, 2 to the x power equals 32. And we cannot solve for this whenever the x is in the exponent like this. So what we have to do is we have to rewrite this as a logarithmic function, or logarithmic expression. So we would have log base 2 of 32 equals x. And when we have log base 2 of 32 equals x, we have it solved for x. Now, we normally want to get a decimal approximation for this. And if you have the really fancy new TI-84 calculators, they will let you type something in with a different base. But if you have the traditional TI-84 calculator like I have right here, whenever you type in log, it doesn't give you any option of changing the base here. It just is a common log. So what we have to do to be able to get our answer here is we have to use what's called the change of base formula. And the change of base formula simply tells us that if we have log base b of a, that is equivalent to the common log of a over common log of b. Or, rather than using common logs, we could also use natural logs. We could say natural log of a over natural log of b. So, in this case where I'm trying to solve this equation, I want to get a decimal approximation, I need to type into my calculator log of 32 divided by log of 2. And if we do that in the calculator, we will have log of 32 divided by log of 2. And you can see here that we get 5 as our answer. Notice that if I had typed this in with natural logs instead, natural log of 32 divided by natural log of 2, I would also get 5. So you can use either for your change of base formula. So 5 is our answer for this equation. Here we have example 7. And this time it's a little bit more complicated. We have 3 to the x minus 2 equals 45. Now we don't see parentheses here, but whatever is in the exponent we assume is sort of in parentheses. So when we rewrite this as a logarithm, we will have log base 3 of 45 equals x minus 2. At this point we can get a decimal approximation from our calculator. We will have to type in log of 45 divided by log of 3. And when we do that, we get approximately 3.465. Keep that number in your calculator so that you don't have to round, although it's not matter for this one because we're just adding 2. So to finish solving that, we would now add 2. So we have 5.465 is equal to our x, and that would be our solution to this equation. Here's our next problem. We've got 3 to the x power plus 9 equals 24. Before we can rewrite something as a logarithm, we need it to be in exponential form, and this plus 9 is a problem here. So what we should do on this problem is we should subtract the 9. So that would give us 3 to the x power equals 15. Now at this point we can rewrite as a logarithm. So we will have log base 3 of 15 equals x. If we have the older type calculators, we now have to do a change of base formula. So we will have log of 15 divided by log of 3. And you can see there that we get 2.465 approximately as our answer to that equation. You can always check yourself here. 3 to the, I'm going to do second answer so that value's not rounded, plus 9. And you can see that we get 24, so we know that we did the problem correctly. Okay, for this next problem, we have log of 5x plus 4 equals log of 2x plus 18. Now, in order for these two things to be equivalent, the expressions inside of the logarithms have to be equivalent. So what we can do in this case, because we have logs on both sides, we can just drop the logs. That is a phrase that some of my students in the past have thought has been pretty funny. So we drop the logs and we have 5x plus 4 equals 2x plus 18. Now you can only do this whenever the logarithm is on both sides. and everything that you have is inside of the logarithm. So you will subtract 2x here, so 3x plus 4 equals 18. You'll subtract your 4, so 3x equals 14. So x equals 14 divided by 3 for this equation. Okay, sometimes we need to use what we're given. We're given a logarithm and we have to use exponentials to solve. In this case, we've got log base 5 of x equals 20, so we need to rewrite this as an exponential. We would have 5 to the 20th power equals x. So our answer here is 5 to the 20th power. Now if we type that in, 5 to the 20th power, we're going to get a really, really large number. So it's okay with me if you want to leave it like this, or you can write 9.536743164 times 10 to the 13th. Or you can even move that decimal and you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we would have 9, 5, 3, 6, 7, 4, 3, 1, 6, 4, 0, 0, 0. We'd fill those extra spots that are empty there in with zeros, and this would be our answer. Okay. For number 11, we're dealing with a natural log. So that means the base of this log is e. So that means we have e to the 2.5 equals 2x plus 3. E to the 2.5 looks difficult, but it is just a number, so we can type this into our calculator. So if we do e to the 2.5, we get 12.182. And now we just have a simple two-step equation. We would subtract our 3. So that would give us 9.182. And we would divide by 2. And when we do that, notice that I went ahead and did this in the calculator so that I did not have to round at all until the very end of the problem. I get 4.591 as my x. Okay, in this case, we need to rewrite as a logarithm, so we'll have log base 8 of 1 over 512 equals x. I mostly gave you this problem so that you can see what type of answer we get here. You're going to have log of 1 over 512 divided by log of 8, and that will give you negative 3. So you can see you can get a negative with it. Okay, this problem is a little bit different. We're going to have to rewrite this as an exponential, so we'll have x to the 1 over 50th power equals 5. Now, in this case, we need to solve for that x still. So we have to do something that will get rid of the 1 over 50th power, which we could take a 1 over 50th root, but that is difficult to do. So the other thing that we can do is we can raise this to the 50th power, because whenever we have exponents like this, 1 over 50 times 50 just gives us 1. So we'll have x to the first power, which we don't have to write, is 5 to the 50th power. That's going to be such a large number that I'm just going to leave it like that. But you could get a calculator expression for it if you want. You can see here we've got x to the 9/4 equals 20. To get rid of something to the 9/4, we would raise it to the 4/9 power, because whenever we multiply 9/4 times 4/9, those all cancel and we get 1. So this would be x equals 20 to the 4/9 power, which we can do in our calculator. 20 to the 4/9 is 3.786. And then our last example here, we have x to the 10th equals 3. So we could raise this to the 1/10th power. So x equals 3 to the 1/10 is 1.116.